Okay, I hope everybody had enough time to answer all the quizzes. So let's begin today's lecture. What we have taught everybody last time is everything about rigidity. We talk about how to understand persistence length conceptually. It's the distance for the chain to flex, to bend, etc. So we know persistence length is a good parameter to describe how segmental rigid your chain, right? And we gave everybody a little bit example what is persistence for length for several polymers, such as polystyrene. We talked about persistence length is only about 7 angstrom-ish, so it's very small. Where some of the polymer can be much more rigid. Those are DNA molecular that has persistence length is much higher. So we have a little bit left uncovered is Wong-like chain model. So this is something I want to wrap up before we talk about radius gyration. So what is a Wong-like chain model? So everything we have talked about in the last lecture is based on chains that are reasonably flexible. But there is also a chain that is not so flexible. So these are a few examples we showed here. You can see the persistence length LP can go anywhere from 65 angstrom all the way up to 200. So those type of polymer, they are not easily described by those flexibility of the backbone and chain, etc. Because those are typically polymer with a lot of conjugation along the backbone, which means they have large bulky groups such as phenyl rings, such as double bond strands, etc. So the better model to describe those short rigid chain is called Wong-like chain model. As the name suggests, this is basically saying your chain is basically like more rigid, behave like a wall. So let's focus on this plot, take a little bit. So I'll explain what you are looking at. So this plot end-to-end distance divided by LP square. So textbooks use the end-to-end distance interchangeably. Okay, so this would be describe NL square. LP, we all know, is not dependent on N. It's a property related to characteristic ratio L. So if you use that equation, H squared divided by LP squared, you will reach N divided by C infinity squared times 4 is what this value is. Okay? And N is number of bonds, etc. So you can see when this is high, that means your chain is long. When this is low, that means your chain is short. Does that make sense, right? So how about x-axis? X-axis plot is contour length divided by LP. Contour length, L, is related to N times L. LP, again, is 2 divided by C infinity times L. So L divided by LP is basically also related to the bond. But easily, the bottom half, you can understand the total length of the chain, right? Contour length is total length of the chain. LP is how long it takes to bend. So if L divided by LP is a large number, let's say L divided by LP equals to 100, 1,000, that means your chain is much longer than the segment it takes to bend. Right? 1 LP is the time taken to bend. If your chain contour length is 1,000 of that, that means there's a lot of twist bend along the backbone. So these are typically the coil-like, what we see. But in the other extreme, when L divided by LP equals to 1, that means contour length and persistence length is the same. So the middle of the curve, L divided by LP equals to 1, basically says the chain is like only this long. If L divided by LP is, let's use the number of 10, that means there's 10 segments of that. So it will be like this. Make sense? If L divided by LP is equal to 0.1, that means your LP is much, much bigger than L, right? Your persistence length is bigger than L. In what scenario you have a persistence larger than segments?
Really short chains.
In short chains or in a rod-like chain, or you can imagine it's like a piece of rod. So this would have persistence length longer than the segment. So L divided by LP. So this we typically call it rod-like chain, where we circle. So the statistical segment is much longer than the chain. Well, on the other hand, this is more flexible. So wall-like chain basically can describe something in between in this region where it's not a coil, but it's not rod yet. So it's semi-flexible where we can use end-to-end distance equals 2 times LC times LP minus 2 times LP square and times this exponent. This exponent is 1 minus exponent 1 minus LC divided by LP. So if you look at carefully, y-axis is basically end-to-end distance. X-axis is basically L divided by LP. So this would be one large number. And don't be scared by this long equation because we can simplify it in two extreme cases. So this equation is the same. Right, like we had. So let's talk about two extremes. What are two extremes? One extreme is when y, in this case y is defined as 2LC divided by K. Contour length, cone segment. So you can imagine when y is much bigger than 1, this basically means your contour length is much bigger than persistence length. That's the extreme of flexible coil. In the extreme of flexible coil, exponent E minus y will be closer to 0. Everybody familiar with what is exponent means? This is a natural logarithm E minus y means exponent of y. Okay, so exponent, let me draw you guys. For some of you, it's a good refreshment, right? So let's use exponent of x. Y equals to exponent of x. E is a natural logarithm, so its value is 2.36, something like that. I can't recall on the top of my head, but it's a number. Then its power of exponent. So this we can plot y, this we can plot x. When x equals to 0, E exponent of 0 is equal to 1. When x equals to 1, this will be the natural logarithm of E. Okay? And when x is equals to 2, this will be E squared, and this will go up very quickly. So what about y equals E minus x? Everybody familiar with the exponent will know that this is the equivalent. E minus x is equivalent to 1 divided by EX. Or let me write it here. E minus x equal to this. Okay. This is just a simple math. They're equivalent, these two terms. So when x is very large, much bigger than 1, we can give a random number. Let's say E minus 1,000. This will be almost 0 because this equals to 1 divided by E power of 1,000. If you use a calculator, this will be enormous big number. Okay, 1 divided by a very large number will be infinitely close to 0, but not yet 0 yet. So we basically say this, we can assume this is the case so that this will be 0, right? LC divided by LP will be 0. when your chain is very flexible. Yeah, Joseph.
So you have LC, Y is 2LC over LK, where LK is the Kuhn length?
Yes, in this case, it's twice of LP.
Oh, Kuhn length is twice of LP.
Yeah.
Got it.
So
Okay.
what length?
Kuhn length. It's just another name. Daniel actually asked me the other day. So, okay, this is a little bit interesting, Amy. This is a very, very interesting. Why? Because they talked about two terms that is almost similar. So, Kuhn length versus persistence length. Persistence length. In normal cases, this is written as LK. This is written as LP, stands for here. And LK is typically closer to twice of LP. And the definition of Kuhn segment is very easy. Defined as end-to-end distance, we can use REE square divided by contour length. So it's a core size normalized by its total length. And you will see that this will be NL square. This will be for free rotation chain. But since we have C infinity here, that means we typically, this is a more generic way we say end-to-end distance. This means LC will depend on the bond angle, so it will be NL divided by tan, I believe it's a tan sine half theta. So this LK is basically C infinity L times sine half theta. Did I miss a unit? No. Questions? But you can imagine this is twice of persistence length in normal cases. I have a slide I can show you guys to make sure I said it right. Right here. Okay, that's the definition of the relation between persistence length and the Kuhn segment length. Now, let's don't dwell on too much because I want to cover this part. So in the extreme case, this will be LC divided by LP. For flexible chain, this will be a much bigger number, right? LC divided by LP could be thousands, millions. So this segment, this part is basically equivalent to 0. So your end-to-end distance, REE, so you can simplify this into 2LC LP minus 2LP squared, 1 minus 0, because this is equivalent to 0, okay? So you can see 1 minus 0 is 1, so you basically get LC LP minus 2LP squared. This we can further simplify because contour length is much bigger than persistence length in extremely flexible chain. So this term, LC, is going to be much bigger. We can write it this way. Is it clear? LC, if LC is much bigger than LP, we can basically write as twice of contour length times LP. And it basically goes back to what we have started with.
So basically you're just saying the second term is effectively 0?
Second term is effective 0. It's much smaller than LC times LP. Right? So in the other limit, in the rigid rods, we can use a Taylor expansion. So this is going to be tricky for those who are not have taken advanced maths, but I'll show you guys. E minus y, when y is much smaller than 1, only in this extreme case, okay? We can use a Taylor expansion, Taylor. It's just a math operation. This will be equals to 1 minus y plus 2y squared minus 3y power of 3. Only happens when y is much smaller than 1. Okay? So we can break down this exponent term into more linear term. And in the board, I didn't even write the third term because this will be negligible because y is a very small number. Imagine it's like 0.01, 0.01 times itself. The higher order term will be smaller than this and much smaller than that. So if we expand what we have on the top, 1 minus exponent L minus LC divided by LP, we will reach this long equation. And if we expand, y minus y is cancelled out, minus 1 plus 1 cancel out. We basically left as y squared divided by 2. And this will be y squared divided by 2, and we define y as 2LC divided by LK times 2. If you add it here, you will reach the conclusion that end-to-end distance equals to contour length squared. And that makes total sense, right? If for a rod, your end-to-end distance is basically contour length. Your end-to-end distance square will be contour length square. Okay, so for those who are interested in understanding a bit more about Taylor expansion, I have some handout for you guys to read a little bit. Any questions so far? Amy?
Yeah, this top set of equations, I haven't even gotten a chance to look at because I was like trying to understand the bottom.
Yeah, just to understand the bottom. The top part is not important. It's just to help everybody to read it because we simplify a segment. We define the y equal to this, so we don't need to write very complex equation. It's so if you use y equals this to replace every single term, it will be REE squared will be LK divided by 2, 1 minus 1 plus. So it's just as simple to read, but nothing useful in that top part of the equation. Okay?
Sorry, could you explain what is contour length? Because sometimes we just use contour length is equal to n times L. Sometimes we need to times we need to.
Right. Good question. So contour length. When does LC equals to NL, and when does LC equals to NL times sine half theta? So this question is very good. I like it. It's very similar to end-to-end distance. Sometimes REE equals to square equals to this, or REE square equals to C infinity NL square. So these two, it depends on the model. So if you have a freely joined chain, when you're no longer constrained by the bond angle, so freely joined chain, you can pull it, then every chain can be lined up to be 180. So it will become that. But if you have considered the freely rotation chain model, you have a bond angle you cannot break. When you pull it, it's going to be a zigzag shape. In that scenario, your contour length will be angle dependent. Okay. More questions? Everybody?
So you said freely rotated was the one where you have to take into account the angle.
Yeah.
And then
and freely joined. Freely joined because your bond angle can be flexed.
So freely joined, you just do contour length as NL. And then end-to-end distances and elsewhere.
Yeah, yeah. Okay, so I know it has been a lot of model, blah, blah. So today we're finally going to teach something realistic. Not just model, not just something is intangible. We're going to measure a size of polymer today. Everybody excited? We can measure them. It's the greatest thing ever. So no more equations, but we're going to measure them. And you guys already see the slides. We said, we talked everything about end-to-end distance. But if I tell you we can't measure end-to-end distance, how many of you are going to throw your notebook at me? 0? Come on, you guys need to be festy, because that means what we have taught so far could be useless. But not the case, of course. Otherwise, we wouldn't taught the same lecture for the past 50 years. But truth to be told, we cannot measure this directly, end-to-end distance square, because there's no good technique. You can find the chain end and put a number to measure it, period. It's just not possible. If somebody told you they can measure it, it's probably a lie, because they can't do that. But we can do it indirectly. What do I mean by indirectly? Is we can use a technique to measure the core size that is very related to end-to-end distance. As a matter of fact, I'll tell you exactly what we're going to do today. We're going to measure a parameter called radius of gyration. Let's try not use a pink color. So we're going to use radius of gyration. Okay? So this is a parameter we can measure. So this is called RG. And if you read other people published work, or in polymer science, this is a parameter you're going to know. This is very important, because this is how we measure the size of a core. It's like you go to a wellness check. That's your height, your weight. These things are measurable. The polymer, we can measure it by RG. And radius of gyration is a parameter we can measure. And I'll tell you directly, RG square is related to end-to-end distance. RG square equals to 6 REE square, average. Okay. So our end-to-end distance is 6 times bigger than RG square. So if we measure RG square, you will be able to get what is end-to-end distance. I know a lot of you have questions about why there's a factor of 6. We're going to discuss it in the lecture as well. But I want to tell you the science first is, if you measure RG, we can get end-to-end distance. They're related. So don't throw a book at me, because what we thought is still useful. All right, so now, what is this radius of gyration? How should we understand it? Is most important question. So let's take a look at this polymer chain again. So this is the show here. This will be one of the atom, next one, etc. So you understand what I mean? We only draw 8 of them as representative. So radius of gyration, basically, it's a measurement of polymer size, but it's more important is average of each monomer units from the center of mass of the chain. It measures moment inertia, so RG square equals to I. This I is called momentum of inertia, and divide by its mass. So let's define what is I and M is. Listen carefully, because this is very important. I equals to summation of mass of your atom times distance to the mass center square. So you have a little bit of mass times R squared. And what is Mn defined as summation of the mass. So questions, anyone? It's a bit abstract, so we're going to do an exercise about one of the exercises later part of the lecture to help you guys understand. But so first, let's understand what is center of mass. So this red dots is imaginary center of the mass of those atoms. So you can make sense of it because it's the center of mass, right? For a given polymer chain, you can find the center of mass by, if you know the location of where each atom is, you can average them out and find where the center. So even in this classroom, I can find the center of mass for everybody. So it's probably somewhere, between Joseph, Amy, Moni, right there. That's the center of mass for the class for everybody, right? Because it's right there. So, excuse me. So now we can get radius of gyration square would be just, we need to calculate what the mass of each element of your polymer, which is we know, and radius r is the center, Ri defined as, not the bond, okay? So if you look at here, Ri defines the vector from the center to where polymers are. So it's the distance to the center. So as long as we can get these values, we can get your polymer property, right? So anyone has any questions? As for now, Amy, yeah?
How did you get N on the bottom in the second?
Oh, this one? Let me take a look. Oh, I see. So in the top, so this is summation sign, right? This means sums of mass for each element. So you can imagine each carbon has, let's assume a mass of carbon C. So the mass, if we just need to get the mass of all the carbon, so it just equals to number of carbon. N is basically number of the chain, right? How many segments in it, number of bonds, times the weight of each bond. On the top, we also have a mass, so we need to sum them up. But because the mass we can cancel out if we have a density term, we were left with just a summation of the Ri square, which is vector square. Does that make sense? So basically the bottom summation is basically N. The mass, the Mi, let me write here, Mi Ri square divided by summation of Mi. So if we know the number of bonds, we can add all of them together. So let's assume each carbon has density of mass unit M0. It's just how heavy each are. Each carbon has one, M0. So if you add all of them together, the bottom will be equals N times M0. The top will be, each one has M0, right? So we have, right, Ri square summation.
Oh.
And we can cancel this Mi and left as N summation of Ri square.
I was thinking the entire summation term was squared, but just the Ri is squared.
Yeah.
Yeah.
Okay, looks like I don't know what you are talking about. I think you understand. That's good. Any questions so far? So that would be definition of radius of gyration. And moment of inertia, you can think about mass times the distance is like, it's a term, it's hard to explain, but you can imagine that would be related to how heavy the things are and what's the distance to the center. If it's more of off-center, then your RG will go up. All right, next. I'll show you a few example radius of gyration for variety of object. What is RG and how related? So some of them you guys can very easy to understand. So Gaussian coil, it's basically our polymer. RG squared will be MB squared divided by 6. So basically end-to-end distance divided by 6, I already told you. And it not only can describe a flexible chain, but it also can describe more complex system like Gaussian star, Gaussian ring. Gaussian ring is just a polymer that is closed. But something that more easy to comprehend is, let's take a look of a solid sphere. So if we have a sphere, I'm going to be terrible at drawing. So I have a radius of r. So RG is actually not the radius of the whole polymer. When you calculate, RG is 3/5 of r squared. Okay? It can be a homework for you guys. And let's take a look at thin rods, and we can work together on this in the class. This RG will be equals to the rod has a length of L, so this would be the radius gyration of RG square, sorry, I missed the square. RG square will be equals to 1/12 of length. So that will be the radius gyration. So that should be roughly equals to, RG would be 1 divided by root 12. So roughly 1/3 of the length. So radius gyration would be 1/3 of L. So this would be the RG. If this is mass center, okay? Give you some idea. So how do we get to RG equals to L squared divided by 12? Let's use this as an example and do some exercise together. Do I have, I don't have anything written, so we can do it on the fly. So let's use this as an example. So we know that in the last slides, your RG squared defined as moment of inertia divided by mass. So this will be the mass, and the top will be mass times r squared, right? So it will be summation of mass Ri squared. So what's the mass for the rod? Let's assume you have a rod length of L. Each segment has density of L. Does that make sense? If we check it, we chop the rod, it has density of L per segment. So what's the mass of the total rod? What's the mass? How heavy? If we say this will be, assume the density, because we say this rod is infinitely thin, so we don't need to consider cross-section, we just need to consider the length. So let's define density per length times the length will be the mass. Does that make sense?
Just be L squared.
Hmm?
You said.
Just the mass, how heavy it is, right? How heavy the rod weight will be depend. Rho defines as mass per length. So if we time the density times the length will give you how heavy the rod is, and length is L, and density is given. We can get the mass of the rod, right? But the top part is a bit tricky. So how do we get this part. All right, this is going to be harder for those who. So how many of you has learned integration? What this equals to? Oh, Winfield, please help me.
Let me make sure I remember right.
Integrate or just x?
1/2 x squared plus c.
Perfect, right? So if you guys should outright a few answers. So this will be 1/3 of x power 3. And anyone need help for this? I'm happy to slow down and explain a bit. That's just the integration and derivative.
I'm confused about the setup here. Like
Which part?
The diagram that you drew, like
Okay.
it's 12, what is that P?
Where is 12?
That's rough.
There's no 12. Where is 12?
I was thinking the thing on the far left was 12. Like
No, it's just a rod with a length of L. It's a rod. We're just going to use a class to calculate what the radius gyration to help everybody understand. And we're going to use the example of just a thin rod. Okay? And we're going to practice this basically equation. So the mass we know is the density times the length. Now the question is, how do we get the momentum of inertia? So that's a bit tricky, because if you look around the rod, imagine this would be the mass center. The center of mass would be half of the length. Does it make sense? If we equal density, this will be half of the density, right? It will be right in the middle because this rod is symmetrical. So weight center is here. But now, the momentum inertia is different at different location of the rod. If you look at here, at the middle, if you look at 1/4 of L, and at the length of this guy, this will have different momentum of inertia. Despite this section, it has a home heaviness or the home weight. So how do we solve this problem? So we actually need to integrate we have to integrate the mass times r squared. Right? Mass times r squared. The mass is, we can define, so we need to integrate it from, because it's symmetric, we can just use twice and only calculate right half. We need to integrate from where the rod is at the center and walk around the rod. We need to integrate the length from 0 to half the L. All right, what's the mass? Mass will be, if we know the density, we turn the dr. Okay, so this is sometimes a bit confusing. What is dr? dr is, if we chop this into short segments, each segment we can call it a small fraction. That's what the integration is. So density times dr and times r squared will be momentum of inertia. Sarah, yes?
I feel like I'm having a slow moment, but I can't remember what you said the significance of the middle of the chain was. I think it had something to do with mass.
Yeah. So let me explain why we need to take. Because when we need to calculate radius gyration, first step is find where the mass center. Then we calculate what's the distance for each element to the mass of center. So the rationale is we find the mass center for the rod, will be right in the middle, right? Then we can calculate what will be the mass times r squared. Because if we know this is the center, then we can calculate for this, a piece on there, we can get, this would be the r. Does that make sense? Say better? So we can calculate what this r squared and this. So we can calculate every single element and calculate the mass center. Because along this rod, each of them will have slightly different distance to the center. We actually need to use this integration sign. And we need to integrate from the center of mass, which is distance of this segment to the center is 0. And this furthest point to the center of mass is half of the length. So we need to integrate from 0 to half. And this is what it basically show here. We need to integrate 0 to half. Mass, this is the mass, is defined as what the segmental length is defined as dr and times the density, n times r squared.
Why are you not integrating R?
Why am I not
It
integrating?
seems like it's outside the term.
Yeah, it's interchangeable. You can move it here. It's integrated based on r, right? Of course. So, and Winfield, thank you. You helped me solve the problem. So, because density we are not integrating, we can pull it out outside the equation. So twice, 2 times density integrate from 0 to half L r squared dr. If we integrate r squared, we're going to get, let me write a little bit taller so everybody can see it. So I equals to 2 times density times 0 half L r squared dr. So this integration we know it's equals to 1/3 of 3L power 2 times density. And we typically write it 0 and half here. That means we need to consider where it starts and where the integration finishes. So we can plug in those two values into r. That will give you 3 minus 2 of L. We can replace r with first value, and second value is 0. So it's basically 0, right? So what this equals to, let's do a math. 2 times density times L divided by 2 cubical. So this cubical will be equals to L divided by 8, right? And divided by another 3 will be L divided by 24. So it's 2 times density times L divided by 24 cubical. Questions? If not, then this will be half 12 of density times. And if we just normalize by the mass, we put it here. This will be density L cubical divided by 12. You can see density will cancel, L will cancel 1. It will be 12 L cubical. And this should be, yeah, I didn't mess it up. See? No claps? All right, I see Sarah is clapping. Good job. So, and it's not that hard, but you have to understand where the center of mass is, then you can do proper integration. So you can, if you want to do a practice, I suggest everybody take a look what is solid sphere, and practice a little bit after the class, how does a radius of gyration. So I'll give you everybody a hint, then you can play a little bit with what the RG of sphere, and you will be understand this RG parameter better. So for a spherical structure, the center of mass will be right exactly at the center of the sphere. Makes sense, right? But for sphere, it's a little bit complex because we need to consider mass of a sphere. So how do we get the mass of the sphere?
Volume times density.
Oh, good job. So we can use mass is always easy. M is equals to 3/4 pi r cubical. That will be the mass of a spherical ball. Makes sense, right? So what about a moment of inertia? That's where it's a lot of tricky is happening. mass times Ri squared, integration. For sphere, it's more complex, because now we need to consider what's the distance to the center. So how do we get momentum of inertia? In this case, we need to imagine an object that everybody have cooked with onions. So when you slice a sphere, you're going to have what? Layers of onion. So imagine now I cut it this thing. Here, I can see a perfect one. Now I can see different layers of sphere. Right? All the sphere shares the same distance to the center. Excuse me, it's not perfect spherical, but you got the idea. So when we calculate momentum of inertia for a spherical structure, it will be all the same distance to the center will have the same momentum of inertia. So how do we calculate the mass of that portion? We need to learn a little bit of what the surface of a sphere. What the surface of outer sphere for this surface area of this sphere in the outer area.
It's not 2/3 pi r squared, is it?
No, this is the volume, 3/3 pi squared. So the surface area of a given sphere should be 4 pi r squared. Okay, if we know this, we can basically get a momentum of inertia because we imagine the spherical structure has a layers of surface. We just need to integrate from the inner area, start with r equals to 0, all the way to the outer area equals to r, 4 pi r squared times density dr. Does that make sense? So that would be the momentum of inertia for the spherical structure. I almost missed the r squared at the end. All right, that's would be the mass, and this would be the r squared as defined by that. Okay, why don't we finish it? Oh, Amy, yes, please.
Using lowercase r and uppercase r, what's the difference?
No difference. I'm just messy. So excuse me. You got me.
And this density is in terms of mass per area?
Yeah.
Per surface area?
Yeah. No, this is actually density per volume because we use density times area times r squared.
What is the r squared under r squared for?
No, this should not be r squared. This should be momentum of inertia. Let's finish it. So this will be equals to 4 pi r cubical times density times dr, integration from r, right? So what is r cubical? Because this is constant, these two are constant, so we can take them out, right? 0 r cubical dr. So Winfield, can I ask you for another help? What is the integration of cubical dr?
R to the 5th over.
Oh, yeah. Yes. Right? And this turns out to be just r/5. Because we need to integrate from 0 to r. 0 is equals to this minus 0 cubical phi. So we can cancel out the last term. So the top part will be equals to 5/4 pi density r cubical. The bottom will be 3/4 pi density r cubical. Density pi cancel each other out. 3 and 4 and 4 cancel each other out, we will be equals to 3/4 r cubical. Right? Did I went too fast? So this would be solid sphere's radius gyration. Yeah.
Do you mind if I take a photo? I'm having a hard time seeing.
Sure.
Thank
Sure.
you.
No problem. Yeah. No. Don't worry about taking photo, etc. The camera should have enough resolution you can
That's
see.
true. I always forget about that.
Okay, more questions? So we definitely will have a final exam on radius gyration. So give you guys a heads up. So you want to practice a little bit. We talked about thin rods. You can go back, play a little bit with. Cylinder is a little bit hard, but you can play with thin disc. This one is easy to integrate. Thin disc is just the disc is very thin. So it's just I wish I have a disc I can show you guys. It's infinitely thin. You only need to consider a 2D object. So you need to know how to calculate the mass of the disc and momentum of inertia. Mass is usually the easy one. Momentum of inertia is usually the harder one because you need to integrate the mass, the segmental mass, dm times r squared. Okay, and I encourage everybody to go play a little bit with it. So, any more questions? Yes, Sarah?
Sorry.
Yeah.
So over here on the board where we came up with density times L cubed over 12, can we just simply take I guess the density term and one L term and make that mass? Because I'm kind of confused how we got the L cubed over 12.
So this is basically momentum of inertia. Rg is defined by I divided by n. So we need to divide n. N is divided by density times L.
Okay.
So basically this goes here.
Right.
You know, I just copy paste everything here. Then this term divided by density times L.
That's right. Okay, I forgot to go back up there. Thank
Yeah,
you.
no worry. So same here. So make sure you got mass right and momentum of inertia right. Please.
For finding the radius of gyration for the thin rod, you multiply by 2 to compensate for the whole length of the rod, correct?
Yeah, because it's symmetric, right? We only integrate from 0 to half L. That's why the integration had an effect of 2 here. Good. Okay, if no more, let's finish today's class. And feel free to chat with me if you need help on answering those radius gyration. I suggest you guys go home, practice a little bit of thin disk. And we can begin the next class. I'll introduce how to calculate that. Then we can serve as a reminder of what we taught today.